And here we go on infrared spectroscopy, which is usually just IR spectroscopy. This is the one I really wish I was there to teach you, because it's kind of fun to stand up in front of class and do all my little funny moves and make a spectacle of myself so that you guys remember all this. But you just have to use your imagination maybe and think of me doing this at home from the comfort of my couch. So IR spectroscopy is based on the vibration of bonds. So it's looking at how much bonds are bending and stretching. And so if you imagine, an arm stretching out from your body, that's kind of what the bond is doing. It doesn't stay static. It's not still. It's actually dynamic. And so there's a stretch there. And when infrared energy is absorbed by a bond, they each stretch or bend in a different way, and we can measure those vibrations or that absorption. And so that's what IR spectroscopy does, is it identifies the type of bonds. So it can tell us if it's a double bond between carbon and oxygen or a single bond between carbon and oxygen. The important thing to remember is that it only identifies polar bonds. So if you have a carbon-carbon bond, it's not really going to tell you much about that because that's a non-polar bond, and it's not going to be able to actually absorb any energy because that stretching is going to be completely symmetrical, and so it won't show up. But if the bond is polar, there's a dipole, and so that bending and stretching is asymmetrical, and the IR spectroscopy will be able to read that. So that's kind of what we're looking at with IR spectroscopy. IR spectrums are often used, or spectra, I guess, are often used as a fingerprint. And so they use this sort of thing in forensics to identify specific chemicals and specific substances because their spectra or spectrum, I can't get the plural and the singular right, but that's okay, is very identifiable. And so if you say, this is the spectrum of this drug, then if you get a reading that has that spectrum, you know that it is that drug. It is a way that we identify those chemicals. So let's take a look. First, we're going to look at, this is what the machine looks like. Again, it's not very exciting from the outside. You put a sample into this machine over here, and you get a readout on the computer. It looks like a lot of these spectroscopers where, you put it in a machine and zap, it shows up on a computer. So it's not all that magical. This is a graph of a IR spectrum. And one of the things you should notice, first of all, is that all the peaks are going down. And so what they did when they first started running IR spectra is that this is 0, the top line, and then all of the peaks are negative. We still call them peaks, even though they're valleys. That's how we refer to them. And so it just looks upside down to a lot of people, but we still read the graphs this way. So in that purple sheet that hopefully Mr. Humphreys has given you, it has various ranges of IR spectra that indicate specific bonds. So this has some listed on it here. The OH, NH, and CH bonds are down in this range, in the 3000 range. And these numbers are in wave numbers, which is the inverse of the wavelength, if that makes any sense. So instead of being in centimeters, which would be the wavelength, it's the inverse of that. And then here are some triple bonds between carbon-carbon or carbon-nitrogen. Here in this range, what is this, like 1500 to 1800, you have CO, CN, and CC double bonds. Those are all double bonds. And then single bonds are up here. From my experience, single bonds are not very useful. This range, for us who are very inexperienced at reading IR spectra, it's very hard to read some of this stuff. It's usually more of these bonds down in this range, the 3000 to 1500 range, where we're going to have data that's usable. So in this case, we know that there are no triple bonds in this molecule, but that somewhere in this molecule, we might have one of these bonds, we might have one of these bonds, and of course we have some single bonds. But again, the single bonds are so many and so ubiquitous that it's really hard to get any information from them. Most of the time on the exam questions, it will actually label which ones you're supposed to identify so that you're not just looking at the entire graph and trying to pick out what's important. Again, in college, you can take an entire semester on analytic chemistry and learn a lot more specifics about how to read these graphs and what they mean and those sorts of things. And we just don't have time to do that in, the 2 weeks that we spend on it. So that's what one of these graphs look like. Again, IR spectra is all about the bonds. What are they, double bonds? Are they single bonds? And a lot of times you're eliminating information and putting that together with a bigger piece of the puzzle. So a lot of times you can't take just mass spectrometry or just IR spectra or just NMR, which we're going to talk about in a minute, and be able to identify a molecule. You have to take all these pieces of information and use them together to figure out what the structure of the molecule is. So don't think that you don't understand it well enough, because you can't. You need all these pieces of information to put the puzzle together. The next one we're going to talk about is NMR spectroscopy.